What I want to speak about today is the materials that you see here in the background. A little bit slower than it should be, but that's because we're going through a Wi-Fi connection. What we can do with these. So these are cholesteric liquid crystal elastomers. I figured that the background of the audience here, I think, is very diverse. So I'm actually not going to speak so much about the fundamentals of these materials, but rather what you can do with them, in particular in the context of strain sensing. But because these are elastomers, I thought to first of all just say a few words about what are actually elastomers. To those who don't know the term, it's kind of the scientific term for rubbers. So we all know what rubbers are. But since it's a summer school, I thought to ask you a very interesting question. And that is a rubber actually a solid or is it a liquid? That isn't actually that trivial to answer. So rubbers really belong to the class of soft matter, where you cannot clearly distinguish whether it's a solid or a liquid or a gas. Definitely it's not a gas. Most people probably say that rubbers are solids because they have a distinct shape, they don't flow. But I tend to adopt the same idea as Mark Warner and Eugene Terentiev adopt in their classic book on liquid crystal elastomers, which focuses on the dynamics on the molecular scale of rubbers. And I don't know how many of you know what rubber really is at the molecular scale, but actually it is a liquid that has been cross-linked. So those cross-linked have the effect that this liquid cannot flow. And as Terentiev and Warner point out, they say that a rubber is a liquid that cannot flow. And that is extremely important. That is behind all the behavior of rubbers, this incredible elasticity that we have. That's because rubbers are liquid. At the molecular scale, in terms of the dynamics, they behave like a liquid. It's just that you have a few cross-links that prevent them from flowing. And this liquid behavior is absolutely fundamental for their behavior, as well as for the behavior of the liquid crystal elastomers that I will talk about today, which then are liquid crystals that cannot flow. So that's quite important to keep in mind. Before going on, I would like to introduce my co-authors, Jan and Rajesh. Jan is a physicist, Rajesh is a chemist. They're both postdocs in my group. And the project I will be speaking about mainly, it's called Reveal. And it has two collaborators who are very important for this project, Matthew and Danielle. And if you look at their affiliations, you see that they're very far from liquid crystals. And there is a very good reason why these are the ideal collaborators for this project. And that is because the Reveal project is about using cholesteric liquid crystal elastomers for strain sensing, for monitoring strain and for detecting strong deformation in structures that are very far from liquid crystals. And I will take the opportunity to point out that Jan and Rajesh should soon get another team member. And we're actually about to announce the position. We are recruiting a person on that project who should really take the entrepreneurial standpoint and take this from research to market, because this is a so-called proof of concept project. The whole target is to bring this to market afterwards. So if you are interested, or if you know anyone who is interested, please contact me and I can tell you more about it. So what is this about? This is an interesting article from 2015 when Obama was still president. And it points out that the infrastructure in the United States is in a critically bad condition. And you might, well, first of all, you probably wonder, what on earth am I speaking, why am I speaking about infrastructure when the talk is about liquid crystal elastomers? I'll come back to that. But you might also wonder, well, this was 2015, but things have probably gotten better. But unfortunately, that's not really the case. This is from last year, and you see it's still a very serious issue. This here is a snapshot from the from the American, it's a report card for America's infrastructure. I took this morning, and you see the scorecard they give. It's like in school. They give infrastructure scores, A, B, C, and so on. And the current score has actually increased up to C-. But you all know that C- is a very, very bad score. So this indicates something, that the infrastructure in the US is in a very bad shape. It's not just about infrastructure. I'm pretty sure you all remember this one from Surfside Condominium, where suddenly half of the building woke up to find that the other half of the building was missing. Almost 100 people died in that accident. And is this only Europe? No, of course not. We are in Italy now, and I think this picture is just far too known to all of you. This is the Morandi Bridge in Genova, 2018, which collapsed. So indeed, European infrastructure and built environment in general has its share of problems as well. So in fact, this is an international problem, and there is a very strong activity to do something about this. And this goes under the name Structural Health Monitoring, or SHM, where the idea is that you integrate sensors into built environment to monitor whether the structure is sound or not. And I highlight just 3 of these items that I think are particularly interesting to address using cholesteric crystal elastomers. But before going to that, I just also want to mention that this is not only about unsound, bad, old structure, but also for healthy structures. So for instance, if a structure is subject to overload, it can collapse. This is a quite recent example in Jerusalem, I think, or West Bank, where a seat bank collapsed because there were too many people. This is a famous example from Katowice in Poland. There was snow on the roof. The roof caved in, 65 people died. A few years back, there was, in Russia, a swimming pool where the glass roof caved in because of too much snow, and a lot of children died. This is from a concert back in Stockholm, my own home country's capital, where Avicii was playing, and people were dancing and in synchrony, and then at some point the platform where they were standing caved in. Luckily, nobody died there, but a lot of people got injured. And this is a quite important issue that we are also looking at here, and that is, after a major natural catastrophe like an earthquake or flooding, now with climate change, flooding issues are more and more important. One of the most difficult tasks is to judge which buildings that are still standing are safe to go into. So in this particular case in Mexico City, this was an office building. People went back in, and 50 minutes after the earthquake, it collapsed. And one of the things we want to work with here is to put up sensors in the building from the beginning in order that people can simply quickly see if, for instance, stories have shifted with respect to each other. So before addressing how to do this with liquid crystal elastomers, how is it done today? The typical way of doing it, we heard a little bit about it yesterday, is to introduce strain gauges or displacement transducers. They are typically piezo-electric or fiber optical. One of the problems with this is that you have one value per sensor. So for every sensor, or for every value you want to have, you have to put in one sensor. And what this article highlights is that this is actually a problem, because you don't know where the problem will occur. You don't know where a crack will start developing. So just to read from the abstract here, which is quite illuminating, damage significantly influences response of a strain sensor only if it occurs in the proximity of the sensor. Thus, two-dimensional 2D sensing sheets covering large areas offer reliable early-stage damage detection for structural health monitoring applications. The point is simply that if a crack develops next to the sensor, you can have a report that everything is fine, but the building is in fact about to collapse. So here they try to do this 2D sensing by combining regular one-dimensional gauges in the network. But we argue that this material is actually the ideal for doing two-dimensional strain sensing, because what you're seeing here is a 2D sheet that is changing its color in response to strain. And you may think that it's very non-uniform, but the non-uniform color is simply because the strain in this sheet is non-uniform. So the color changes really reflect exactly what the strain is locally in every part of the sheet. And to show you that, here Regis has clamped half of such an elastomer under a glass slide, and then he pulls at the other one, and you see that the color of the one that is clamped, it remains. So it really reflects, the color changes reflect exactly the changes that you have locally. And it works, of course, in compression. So here's this pushing from below, and you see there is a local color change where he's doing the compression. So what is going on here? Where do these colors come from, and why do they change? So cholesteric is a type of liquid crystal that is chiral. It is characterized by the director, the average molecule orientation, rotating in a helical fashion. That means that you're getting a periodic modulation of the optic axis. Effectively, you're modulating the refractive index with a certain period, that is the pitch of the helix. And if you ensure that the pitch of the helix is similar to the wavelength of visible light, then you get Bragg reflection, that you may have heard about from X-ray diffraction, or most people at university learn about Bragg diffraction when they study X-ray diffraction. But you can, of course, have this at any wavelength. It just depends on whether the structural periodicity is similar to the wavelength that you're interested in. So that's what's happening, and we heard this morning about the colloidal crystals. It's exactly the same thing in terms of there you have a period of particles, periodic particle arrangements with the period of visible light. What is different here, there are two different things that are quite important. One, this is a helical structure, which means that it breaks mirror symmetry. It is chiral. So the light that is reflected is also circularly polarized with the same handedness as the helix. And the second point is that, what I said in the beginning, this is a liquid that cannot flow. And liquids can be deformed. That's why rubbers are so incredibly deformable. So that's a huge advantage to any crystalline system, including colloidal crystals, that you can stretch these very, very easily, and they don't break, but they respond very strongly. So, yeah, you also have a viewing angle dependence, because the apparent periodicity depends on the viewing angle. So you have a blue shift if you look at a different angle, but that's not what I'm going to focus on here. What I'm going to focus on is simply that when you polymerize this cholesteric liquid crystal into a rubber, which means that you're adding crosslinks, about 10% crosslinks, then you're coupling this selective reflection of light of a certain color and polarization to mechanical deformation. So let me illustrate how that works. If we take our films and we look at a cross section, let's say we're looking along the film. So the helix has been aligned perpendicular to the film. I'll come back to that in a moment, how this happens. And let's say we have, as in the movie I showed you, we have programmed the helix to start reflecting red in the beginning. Now you start stretching this. And a rubber has what is called a Poisson's ratio of about 0.5. And that means that when you deform it, it deforms roughly under constant volume. So if you make it longer in one dimension, it has to get compressed in the opposite. And that's exactly what we are using here. So if you stretch in this direction, you automatically get a compression in the opposite direction. And because this helical structure has been cross-linked and coupled to the deformation of the film, a compression in the film also compresses the helix. And that means that your color is blue shifted. The reflected color is changed, the wavelength of reflection is changed to shorter wavelengths. And that's the cartoon version of it. And here's the real version where we are stretching the film using a force gauge. Thanks to Juicy for that, because that's her group who lent this to us. And as you see on the top left, you see that the color changes continuously. This is a liquid, remember, from the red that we started with all the way until blue. And at every point, we can correlate the color with the force that we're applying, with the stress that we're applying effectively. So this is actually quantitative, meaning that we can really use the color to measure the strain. And this is a curve that shows you that up to an engineering strain of almost 2, the data, the color change data, so this is obtained with a spectrometer, match almost exactly the theoretical prediction, which is the dotted curve. And that theoretical prediction comes from Marco Warner and Eugene Terentjev. So how do we make CLCs? I won't go into the chemistry very much, but if there are chemists here, at least you see which molecules we are using. These are pretty classic nowadays in the field. A lot of people working with CLCs or LCs in general are using these. The one thing that maybe is not always used is this one, LC756. You can have other ones. The point with this one is that it's chiral. So in contrast to the LCs we heard about yesterday, which were nematic, this is a chiral nematic. So you need to add something chiral that leads to this, that induces this twist, the helical twisting. Then you can do what we do in most of the movies I showed today. Here we have a 2-stage crosslink. So we actually have a first crosslinker that is mixed into the system, and it forms a thiol click reaction that gives a first network. And then we can do a second cross-linking by UV irradiation. We also add a photoinitiator. In this case, we actually first polymerize or connect these not into polymer, but into an oligomer. And then this oligomer can then be processed and eventually cross-linked into an elastomer. In both cases, we dissolve these components, whether as an oligomer in dichloromethane or these individual components into toluene. So we start with an isotropic solution, and that means that this is how easy it is to make these elastomers actually. You simply have this solution, you pour it into a dish. Because we have this network forming, once the liquid has spread, it cannot retract. But then the solvent that is volatile, it evaporates, and this means that the film gets thinner, and that is very important for the behavior. And you see after a night, or actually after already a few hours, you just take out the film and it has the red color. So that's how easy it is to make these. And the question is, of course, well, how do you actually get the helix aligned? Because remember that there is an important viewing angle dependence, so it's very important to have the helix aligned. And also, of course, you want to have uniform response. The whole film should respond in the same way. And if we start from an isotropic solution, that means that, okay, once the solvent evaporates, then of course the cholesteric liquid crystal will form, but the helix can form in any direction, right? You have phase separation. In any direction, you have helices forming. How does this work? Well, the trick is this part that I mentioned, that we are evaporating solvent in one direction. This is called anisotropic deswelling. So if you have here, for instance, a helix that is inclined like this, it's not what we want to have it. But now you're evaporating the solvent, and because you have the first network, it cannot shrink in the lateral dimension. So it can only shrink in the vertical dimension, and that flattens out the molecules. So they end up being in the plane, even if they were not aligned initially. And then the question is, of course, well, how is the helix now? You might think that it's like this red arrow here, but that's actually not true. That's just because I drew one very simple cartoon for the helix. But you have to remember that the entire system has, of course, it's not just one cartoon, it's everywhere. So the helix is actually vertical. No matter where the helix, in which orientation the helix started, you get a vertical helix. So this anisotropic deswelling aligns the helix along the deswelling direction, and it also shortens the pitch. It compresses the helix. So you have to tune everything a little bit in order that the final state is read as you want it. So now you might think, okay, this is nice. We're working with rubbers, and I want to do something with structural health monitoring. We're dealing with concrete structure. Concrete isn't elastic. What on earth could I be doing with something that needs of tens of % of strain in order to show a color change? Well, we are actually not targeting the elastic response of concrete here. We are targeting the response when concrete fails. We're targeting cracks. So the point is that you put this type of liquid crystal elastomer on the sound structure, and if a crack forms, the expansion within the crack is immediately several 100%. So you will very quickly see a very strong color change in the crack. You can also apply these on existing cracks once you have seen them in order to monitor whether the crack grows or not, which is extremely important in order to assess whether a crack is dangerous or not. So that's where what we are heading at. Now, just a few words also on a slightly different approach. I mentioned we can also use an oligomer. And if we do that, then we can make fibers. So if we take a droplet and we dip a spatula in it, we can just easily pull out filaments. And we have developed this into a method that really works quite well for making long-scale fibers. And there you can see here that as you stretch the fiber, you have the same effect with a color changing from red initially to throughout the spectrum. And this is more macro. That was a polarizing microscope. This is just a regular camera showing that you can see the color change on black background, but actually even on white background. A lot of work on structural color always has black background because the structural color isn't very visible. But actually here it is quite visible even with the black background. And because these are fibers, we can do different things with them. So we can weave these into responsive fabrics that then did change their color in different ways, in different directions, depending on how you stretch them. And you can even sew these. So this is me sewing one of these fibers into a cloth during the pandemic. And it's just regular hand sewing. And in the end, you get fabric that has a color responsive thread within it that then shows you how the fabric is being stretched. And by sewing it, for instance, in a particular shape, for instance, a curve here, then you can simply, by looking at how the color changes in different parts of the thread, you can just adjust, you can determine how the fabric is being stretched. And you can launder the fiber as well. So we did for the paper, the reviewers wanted to have some endurance tests. So we did 100 stress strain cycles without any change. Then we did 10 laundry cycles and another 100 test strain cycles, stress strain cycles, and there was really no change. So they're very, very durable. What can you do with this? Well, obvious thing is in medical use, sports use, for instance, compression stockings, where you could then immediately see whether the compression is appropriate for the person wearing it, because you just look at the color. But there are many, many other possibilities. And this is just some indication on prediction for the global smart fabrics market, which is, of course, comprising many, many more things. But the nice thing with these is that it's, as you saw, it's very durable. It's completely washable. You don't need any electronics. You don't need any batteries. And it's an elastic, it's a rubber band, basically. So very easy to integrate. And this opens a lot of opportunities. So let me conclude. I hope to have convinced you that the mechanochromic response, this color to this deformation coupling of cholesteric liquid crystals is quite easy to make, to produce both in sheets as well as in fibers or threads. This anisotropic deswelling that we use for aligning the helix, it's very easy to use and it is scalable, so we can really scale this up out of the lab. And there are really enormous application opportunities in structural health monitoring and very many other aspects. So I hope this, you may also have some thoughts about how this can be used. So thanks a lot. And of course, if there is any questions, I'd be happy to.
Oh, just a simple one. In all these applications, you still need a spectrometer and some electronics to detect the formation in real time. Mm-hmm. So how do you apply that to fabric, for example, or to an unknown location of a crack breach?
Yeah. So for the fabric, the main purpose is to make this visible to the eye. So for instance, if you take the compression stockings, the idea is simply that you design it so that the patient can just look at the color by their eye. There's no need to measure anything. We don't need that level of accuracy there. For the structural health monitoring, we would have cameras. If you can mount a camera permanently, you would simply do that and you look at the color. In some cases, you would have drones. So drones are already being used a lot in structural health monitoring. And they are all equipped with cameras. So, and you might even have a spectrophotometer attached to it as well.